Today our basic topic is going to be conductors. Okay. Now I am assuming everybody knows what is the difference between conductors and insulators. Let us look at why conductors behave differently. Okay, and we will look at a bunch of properties for conductors. So we are going to use Gauss law to understand conductors better. In fact, the most important place where Gauss law is really used, apart from some silly set of things like spheres and infinite cylinders, you don't have infinite cylinders generally, right? The real place where Gauss law is going to be used is in conductors. Okay. Now, the main difference in a conductor and insulator, if you take a conductor and insulator, is obviously a conductor conducts. Okay. But that's, why does it conduct? Conductor conducts because if you take this, the atomic structure, think of the atoms and the shells, the electrons that are in the inside shells. Now they are not going to move in a conductor. It's a lattice. It's like a crystal structure. Okay. So all of these atoms are in fixed places. Now there would be some electrons roaming around. If you take copper, for example, the inner shells would not be around this atom. But the outer shell electrons are relatively free. In the sense, they would be going around like this, but very quickly they may jump there and then they could jump here. They can't just run away fully. Okay, we will see that as we move on, that electrons have to be in specific orbits, except that it is not going to be this clear, it won't be like this specific in orbit. But what happens is that all of these things together, we call it like a conduction band. All of the shells effectively join up together, and so the electrons can be anywhere in the metal. We call them free electrons. Now, free electrons does not mean they are really free, in the sense they are not free of these atoms. They are still around these atoms, except it is very easy to move from one atom to another atom. At any particular point of time, they would be around one atom. In fact, they are so free to move that we stop worrying about the fact that they belong to an atom. We start thinking about the fact that they are just going around the atom, all around. As long as, so the way we are going to picture this is to say, I have this bunch of, well, not just nucleus, but atoms with a set of electrons that are fixed, and a lot of electrons which are not really going to be, don't belong to one of the atoms. Now if you took a typical regular atom, let's take a gas atom for example, an electron either is part of this or is completely free. Suppose I pulled out an electron, I have ionized it. Now once an electron has been ionized, it's actually free to go anywhere, and unless it gets captured by something else. If I have an electron hanging around which doesn't belong to this atom, there is no particular reason that it can go here but cannot go there. Obviously it can go all over. Just imagine an atom. If I had an atom here, this atom could go there, it could go there. It's not like this is a very important special place for it to be, but that is not, right? If it was completely free, which is how we are going to treat conductors, you must think in terms of them being almost completely free. But if you think of them as always, I mean, if you think that it is perfectly correct that they are completely free, there is a problem. If they are completely free, they don't really belong to the atom, to any of these atoms, then they could roam around, and they could also roam around. You understand? But that doesn't happen. They don't come out. They can roam around from here till there, and then they can roam around from here to there, and so they can only be inside the metal. Okay, so the proper way to understand it is it's actually here, and it with almost very little energy, it can move from here to there, and then there, and then there, and then there. So it is like it is roaming all over, but it is not leaving the atom. It can go from one atom to another atom, and then third atom and fourth atom, and each of the atoms has enough space around. The reason I am insisting on this is if you think of conductors as being this, that is a sea of free electrons. In fact, that is how most textbooks would write it. What is a conductor? A conductor has a bunch of atoms as part of the crystal, and the electrons have basically become free. That means it's a sea of electrons. Now here it's very useful because it's a good way to understand conductors, but after a couple of months you'll be doing semiconductors. And there's no way you can understand semiconductors if you thought of conductors like this. So it'll land you in trouble when you get to semiconductors. So this is the correct way. And always we also know that electrons are going to roam around atoms at various energy levels. Once you pull an electron out, then this is free. There are no energy levels after this. It's been ionized. These guys are not ionized. They just are relatively free to move from atom to atom, whereas the inner electron, so imagine an electron that is inside one of the inner shells. This fellow is not free to move from here, this atom to another atom. Okay, so you can, I mean, you already know a lot of this because you see that for any kind of chemistry bonding, for example, electrons that are going to roam around this atom, generally when it bonds, also roams around that atom. Right? So it is basically between these two atoms. It doesn't mean it is between these two atoms and if you move away these atoms, this electron will just fall off. That's not that way between. It just means that sometimes it will be around this fellow and sometimes it will be around that fellow. Okay. The probability tells you that there is some probability to be here and some probability to be there. Similarly, when we say free electrons, there is a lot of probability for the electron to jump from one atom to another atom. So it is equally probable, if it was going around this atom, it is almost equally probable to that after a little while you will find it in the next, around the next atom. So that means if I had a long metal piece, I have an electron that is roaming around here. After a little while, it could easily jump here with no extra energy required. On its own, it will keep jumping.
So where does it jump?
Why does it jump? Because it's very easy. Like, why do I walk? Why are you not walking? Why do I walk? I'm walking here, right? Because it's a good question. Why do they jump? Because for me to stand here or to walk, I don't require additional energy. But if you have to keep getting up every time, you're sitting down and every time you have to get up, now you have to spend energy to get to this point and then walk from one seat to another. The amount I walk from one place to another is obviously much more than the amount you will be moving around from one chair to another. Because you can't just move around in your chair just by shifting yourself. Because right now that's not the way the chair structure is. So every time you want to move from this chair to that chair, first you have to get up. So that means you have to get more energy, then you have to move this way and then you have to lose the energy, right? Now to gain energy, to lose energy means obviously you require energy to gain that energy. And you don't want to gain energy already, you like to be in the lowest energy state. So things like to be the lowest energy state, so they were not going to get energy and then shift. So electrons which are in the inner shell, if they want to move here, so think of it this way. Here is an atom. So let me say that this shell, this is one shell, so that is a nucleus. Okay, so there is one shell here and it is full. There is one shell here and let us say that you have got 2 electrons here. And then there is a nearby atom. If I had a nearby atom, so let us say this was the nucleus, shell is full. And this shell has 2 electrons and a lot of spaces. How many spaces in this? Well, it should have 8 overall, 2 is filled. So 2 are filled. So how many more left? 6. So I have 6 boxes I'm going to put in. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, now can this electron jump here? Yes, not too much of a problem. And its energy when it was there is the same as its energy when it is here. In the jump, actually it has not really had to pull in a lot of energy. If you want this guy, you can say, well, I have so many spaces, why can't this electron also jump here? Okay, now that is not going to happen easily because first of all, to make this jump or make this jump, there is also space here. 1, 2, 3, 4, 5, 6. I am using these boxes to say that there are empty spaces. There is nothing there. It is just that you are allowed 8 spaces. That's atomic structure, right? So this fellow could jump here. That requires additional energy because this is lower. So think of it like you are at the bottom of a hill. Now you can walk across. If you climb to the top of the hill, then you can walk across and then get to the bottom of the hill if you want to. But you have to climb to the top of the hill. Requires a lot of energy. You are already at the top of the hill. You can just shift around a little bit. You just have to walk from one point to another. Now this is a lot easier than climbing up. I am explaining what the sea of electrons model means really. Okay, even the sea of electrons even for metals is not completely correct. It is broadly correct. I am going to use it. Okay, I am just saying don't assume sea of electrons means this metal has given it up and these electrons are floating across. Here is one atom, there is one atom, this electron is there. No, this electron is still here. Periodically it can jump there and jump there. It's very easy to jump. It is as easy as my walking from one place to another. All of you will probably find it very easy to walk on playing floor. You don't mind too much walking, right? Because it's the same level. You're not really spending too much potential energy. But climbing stairs, I'm assuming most of us don't like very much. No? Do you prefer walking? Like, would you prefer walking from here to there or climbing stairs which would be similar in terms of height? Which would you prefer? Walking. I mean, this guy wants an escalator. Okay. So clearly, it is obviously that if you want to climb stairs, you have to change energy levels. One, you have to gain energy, which is also something most objects don't like. We like to lose energy, we don't like to gain energy. So if I have an electron in my inner shell, it would have been simpler if I had space here. It would have been happy to jump. With atoms, you must understand that it can jump from here to there without really going through all this. Looks a little weird, but it can, no? That's what is called tunneling effect. We don't know how it actually does it. We know that it is here, after some time it is there. Now our physical model is to say from here to there means it first went out and then came in. If you want to think of it that way, think. But the real point is, it was here, it had some energy, it is there, it has some energy, same amount of energy. If there was empty space, this electron would have happily moved there. But if there was empty space there, probably there is empty space here. And if there is empty space here, first this electron will jump down, which means there is no more empty space. So in general, you don't have any of the inner shells with empty spaces. All the lower energy shells or lower energy orbitals are all filled. This is something you already know, right, with chemistry? I'm assuming everybody knows this, right? So since all of this is completely full, if an electron needs to make a jump, it can only make a jump from the valence shell, the last shell. And for metals, typically out of 8, maybe 1, 2, 3 will be filled. Out of 8. Which means mostly this is empty. So if this guy wants to jump there, will there be space? Do you think there will be space in that shell? Yes. So why should it jump if, well, it doesn't matter. Why should I stand here? I could have stood there. This is the same energy level as that. But how long will I stand there? I am feeling bored. So I stand here for a little while. After some time I get bored with this, I go there. Okay. Generally random motion. I keep walking randomly. It's not like if I stand here, it is better than if I stand there. Now you just put some staircase here. Most of the time I'll stand here. Because that means climbing up. Do you understand? That's it. Simple. The basic logic is they are all at the same energy level and there is enough space here. So even a slight push, what's a slight push? It could be an electric field. Well, if this is an electron, electric field like this won't push it that way. Electric field like this will push it that way. Why? Negative charge. Okay. But suppose I put an electric field, this guy will want to jump. Okay. Very little electric field is good enough. Many times you don't even need an electric field. This guy already has some random motion. That is good enough to make it jump. I want to go that way, go. Because there is a space there. Okay. Now, the model that we are going to kind of pretend like it's correct is this model, which is to say all these pluses are fixed. They have given up their negative electrons and that has become like a C, which means these electrons are free floating objects that can roam around everywhere. Then the question you will ask me is, if it can roam from here all the way till there, why can't it just come away? Because actually it cannot roam around like that. It can only roam from atom to atom, and here the atom ends. Now I can't jump to that fellow because there is nothing, no other atom. There are other types of atoms, but not like, let us say, iron atom or copper atom or any of these. Is that clear? But for all practical purposes, since it can move from one atom to another, it can roam all over the metal. I'm just saying that it is not, I'm not saying something different. I'm not saying that there is no C. It is like a sea of electrons. Like. You understand? That type of sea instead of that type of sea. Because this kind of sea would mean it can just fly away. This kind of sea means actually it is bound and then there. This kind of sea means the electron is ionized. That's a lot of energy to pull the electron out of the atom. You have not pulled the electron out of the atom. The electron is still bounded to the atom. No extra energy. Instead of being bounded to this atom, now it is bounded to that atom. You understand what I am saying? Okay, but this is very easy for the electron to move from one atom to another. And so, if I had like a lattice, all metallic solids typically will form a lattice, crystal lattice. So, electron was roaming around, then it went there, then it went here, then it went there, then it came here. Okay, this is what it's doing, random motion. The more you heat it up, more it's running around, if you can think of it that way. But that's not the only thing that's running around. Actually, more when you heat it up, the whole atom is shaking. But you can think in terms of the electron basically jiggling around, moving from one atom to the other. No particular direction. So what happens is, if I took this metallic piece, from this atom one electron jumps over there, but from this atom one electron jumps over there. And then from here one jumps here, and from here one jumps there, and from here one jumps there, and so on. So effectively, if you think in terms of what is overall happening, if you take this cross section, there have been, let us say, a couple of million electrons that jump over from this side to that side, but a couple of million electrons jumping over from this side to that side. So if you actually look at what is the net transfer, turns out to be 0 or nearly 0. It won't be perfectly 0 every second, but if you just wait for like an averaged out effect, it is generally 0. In fact, even if you take over a 1 second period, that's a good enough average, because this whole thing happens really quickly. Okay, so I hope you have got a general statistical picture of what is going on. There is a lot of randomness, but electrons are very, very mobile. They can easily jump from one atom to another, unlike in an insulator. Now the electrons are bound. The reason in an insulator they cannot jump is all of these are almost full. Otherwise they probably created a bond. And if they created a bond, then it is anyway occupied. Once it's occupied, an electron from there can't jump here because there is no place for it. Okay, then why can't it jump here? Because that's ionization. That requires energy. Jumping from here to there doesn't require energy. But jumping from here to there, basically you pull the electron out of the atom. Right? That requires a lot of energy. So can you ionize electrons from an insulator? Yes, you can, but you need to spend a lot of energy for it. So when electrons move from atom to atom in a conductor, are they ionized? No, they are just what we call in a conduction band and very easily mobile from one atom to another. That's why they cannot, if you want to pull the electron out of the metal piece itself, that again is ionization, still requires a lot of energy. You will learn that it's possible, even if you shine light, it's possible. What is that called? Photoelectric effect. Now photoelectric effect is ionization of the electron. Electron jumping from atom to atom inside the metal, not ionization, because you are just taking it and putting it there, no big energy change. Pull the electron, huge amount of energy, jump, no energy change. Is that hopefully clear? It is in fact less energy change than going from one orbital or shell to another. Obviously if you shine light, you can make it go from a lower energy level to a higher energy level, right? Now even that requires h nu, amount of energy required to make this jump. Now that jump of energy, even that is high. You don't even need that much. Okay, because it's the same energy level, so it just simply slides across. So the main thing about electrons in a conductor is that electrons can move very, very easily. I hope you understand why, but they can move very, very easily.